Hello students, welcome to one more class of probability theory and stochastic processes. In this class we will be discussing about joint distribution function. Till now whatever we have discussed that was like just distribution function we know, but why we should go for the joint distribution function, that we will be discussing in this class, and we will see the properties of joint distribution function. When we will go for the joint probability distribution function, when we have two different events on the same sample space, that time we will be going for the joint probability distribution function. And both the events will belong to the same like sample space, then only we will be going for the joint probability distribution function. For example, if I take two events, that is, for one event is a is nothing but its distribution function is given by x less than or equal to x. X is a random variable and this small x is the real number. B also same thing. One more event B I am taking, where I am taking the distribution function in the form of y less than or equal to y. This y is nothing but it is the random variable, and this is a real number. So two different events I am taking, and these two events, uh, this A is one event and B is one event. These two events should belong to same sample space. Then only we will be calculating the joint probability distribution function. Hence, if I am defining the probability distribution function of this first event A, that is fx of x will be equal to probability of x less than or equal to x. In the same way, I will define the distribution function for the event B, that is fy of y will be equal to probability of y less than or equal to y. So we have defined the two distribution functions. Now, as it is a joint event, how to define this joint event? Because A and B are belonging to same sample space. That is the reason we are defining the joint event. Joint event is defined by x less than or equal to x, comma, y less than or equal to y. So in this way we are defining the joint event. For this we are supposed to write the distribution function, that is called as joint probability distribution function. So I'll be writing that fx of y x comma y joint, because both the random variables I'm considering and both the real numbers. So joint distribution function, that will be written as probability of x less than or equal to x comma y less than or equal to y. And always this is nothing but joint. Whenever we are finding out the joint probability distribution, it is nothing but it is like giving the intersection of both the events. It is the common joint, okay, which are the two in those A and B, which are the things that are occurring commonly. So probability of A intersection B, and this A intersection B must be defined on a single sample space. Next, just think, uh, Just find out in the real time what could be the examples of joint events. Joint events. Whenever joint events are there, then only we will be going for the joint probability distribution functions. So just think of some of the examples where joint events will be there, where two events will be means they belong to the same sample space, but with different we can define it by different variables. So just think of the examples of the joint events. Yes, hope you people have thought the examples related to the joint events. There can be so many examples related to the joint events. Whenever we are playing, like just if we are um, playing cards, when like when like one event will be related to the another event, that time we can find out the uh, intersection, that is the just like what could be the intersection between the a intersection two different events we can take here, a uh, a and a intersection b, and we can find out the joint events. So in this way also we can find out the joint events. There are just you can think of any number of examples of the joint events. For this, we will see for the joint distribution function which we have discussed just now, we will see different properties of joint distribution function. So if I'm taking, just recall your properties of the distribution function. In the same way, we will be defining the properties of the joint distribution function. So if I'm taking fx of fx comma y, uh, minus infinity, that is x is less than or equal to minus infinity, y is also less than or equal to minus infinity. That time, because there are no real numbers less than minus infinity, less than or equal to minus infinity, that's why I'll be taking it as 0. I will extend this property a bit and I can say x comma y of minus infinity comma y, this is also equal to 0, because this is less than or equal to minus infinity means there are no numbers here, and intersection with this means there will be no number. That's why it is just equal to that distribution function value is just equal to 0. In the same way we can write fx comma y of x of minus infinity, this is also equal to 0 because y is less than or equal to minus infinity. There is no number that is existing less than or equal to minus infinity, and that intersection with x also there will be nothing. That's why it is equal to 0. And second property, just if we take both numbers up to infinity, x also up to infinity and y also up to infinity, we will be getting 1. As we had got in the distribution function property, fx of infinity is equal to 1. In the same way, f x comma y of infinity comma infinity is equal to 1. Because total distribution function, anytime this will be equal to 1. And always the interval, it will be uh, will be between 0 to 1. So I can write 0 less than or equal to fx of y, x comma y less than or equal to 1. That's why like it is propagating between 0 to 1. Always the interval will be between 0 to 1. As the distribution function was also monotonously increasing, this joint distribution function is also, it's, we can say that it is an increasing function, or we can say it is a non-decreasing function in case of both x and y. That is f x comma y, x comma y is a non-decreasing function of both x and y. So it is a, we can also call it as increasing function, or it is just a non-decreasing function in both x and y. Now coming to the next property. Yeah. See, we used to define the probability value by the interval of x and y. In here also we can define the probability value, that is f x comma y of x2 y2 plus f x comma y x1 comma y1 minus x1 comma y2 x2 comma y1. So this will be equal to probability of x1 less than x2 y1 less than y2. This is nothing but whenever we used to write single probability, we used to write it as f of x2 minus x1. The same thing I am written in that format of two variables x1 and x2. And last property, f x comma y x of x up to infinity, just this is up to infinity, so it will be just equal to 1. So I can write this as fx of x. In the same way, f x comma y, this x is infinity, x is up to infinity, comma y, if I have, then it will be just equal to fy of y. In this way, like single distribution functions also it can be defined from the joint distribution functions. These are the 6 important properties of joint distribution function. Next, in the next class, we will be seeing about the problems related to this. Thank you.